Differential. This is also pretty straightforward. We know what a rate of change is. Yes, delta y divided by delta x. Right. But if I'm in the neighborhood of a particular value, I already mentioned that the average rate of change would be close to the instantaneous rate of change. So instead of calling this the average rate of change, which is y2 minus y1 divided by x2 minus x1, if I'm really, really close to the value x where I evaluated the derivative, I can say the average rate of change is approximately equal to f prime of x. Correct. As long as I'm very close to the point where I evaluated the derivative. That's what we did with linearization. If I cross multiply. That's what we have. And in terms of a notation, I think your book uses this. Ready? Right, settle down, children. Delta y is approximately equal to f prime of x times delta x. Now, since the change we are talking about is very small, that's the entire point, I can only say the average rate of change is close to the instantaneous rate of change if said change is very small in both x as well as y. To differentiate from the regular rate of change to a really small rate of change, we just use dy is approximately equal to f prime of x times dx. What is the consequence of that formula? Dy is what we call the differential in y. And dx is the differential in x. So what are we trying to say? Well, if I know a function, if I know its derivative, I can determine what would happen if I change x by a tiny amount. What would happen to y if I change x by a really small amount? Have we taken a class in business before?
No.
Nope.
Finance?
No.
This is bio and chem people.
Bio and chem people? Okay. Let's say you want to know the temperature of pizza, whatever. Let's say you cook pizza, you bring it out you pull it out, set it outside, and you try to increase the room temperature by a tiny amount, right? So we want to know how long or how much time is it going to take in extra if I increase the room temperature by a tiny amount. It is going to go up, right? Because for your pizza to cool down, the temperature has to be less than, whatever temperature you brought the pizza out to. But if you keep on increasing the room temperature, pizza is not going to get cold, for you to eat. Correct. So it's going to take longer. So that is a simple example. Since you guys haven't done business, in business there are things called marginal costing, stuff like that. So we want to know how a small change in x will affect y, and x and y could be anything. Good.
How a small change in x affects y.
The differential in y with respect to t. Good. So in terms of the derivative, should I do dy over dx or dy over dt?
dy over dt.
Dy over dt. So if I call this function of t, then using this expression, all I'm doing is changing x to t. So the differential in y is simply f prime of t times the differential in x. Good. If f of t is square root of 1 minus t, what
Wait,
is
wouldn't it
f
be
prime?
dt?
Wouldn't it be easy?
Okay.
That's it, time for 3 variable problems.
Wouldn't that be fun? Top 3.
Oh, God.
F prime of t. How do we find f prime of t? Or what is f prime of t? Chain
I
rule.
don't know why that was.
So I can write this as 1 minus t raised 1/2. Yes? So when you take the derivative, you have 1/2. 1 minus t raised 1/2 minus 1. And what do we do? Multiply by negative 1.
4 over 2.
So then we have f prime of t is going to be equal to 1/2. That's going to be -1 plus t, and that at the very least to the power.
So dy would be 1/2, 1 minus t raised negative half times negative 1. If I move that to the denominator, I've got the dt there. Dy is approximately equal to 1 negative 1/2 multiplied by square root of 1 minus t. Yes.
And this is stupid, but why couldn't we just make tx
We can,
to keep it in the same
Later.
terms?
just to, you know, if you want to, you can change it. I mean, going back to the practical example, even though I could call temperature as x, it's better to call temperature as t.
So you know how it
Yeah.
is, what you're talking about.
So
Making a lot of beats.
here is the question. So I have come up with an expression for the differential in y in terms of the differential in t. So a small change in t, is it likely to increase y or decrease y?
Likely decrease considering we're talking about a negative.
It's likely to decrease because we have a negative. Yes, of course, it could also depend on the type of function. So a small change here, it is going to cause a decrease by some amount here. So all we're trying to say is if I know the derivative of a function, I can measure how things would change. In terms of integrals, we have something like this. You integrate both sides, you would get the integral of a function. In practice, engineering of any sort, there is the concept of relative error. So if you change this quantity by a tiny amount, how much error could you expect in whatever results with quantity that you. So we will do an example in terms of application. One, pure approximation using differentials. Other, an application for this. Yes, Joe.
Okay, so like, are you saying like when t is like increasing, like dy it's like increasing, or like when it changes at all, it's.
It could be different also depending on the function. I'm just saying likely to be because I have a negative sign.
Oh, so you don't
I don't know.
know, okay.
So it depends on the function, right? So we have to look at the function.
Okay.
But in general, this is what we have, dy, differential in y is approximately equal to that. We will do an example on this or two next time.